Hello, I'm Matthew Bunkers, the Science and Operations Officer at the National Weather Service in Rapid City, South Dakota, and I will be leading this teletraining on predicting supercell motion in operations. This will take about 75 minutes, and I thank you very much for taking your time to view this presentation. Now for me, this concept of predicting supercell motion all started with a storm back in June of 1996 near the Black Hills. And we've been predicting supercell motion operationally here ever since the summer of 1997. And the message I want to convey to you out of all of this is if you discover a forecast problem and you are interested in it, by all means pursue it with passion because you just never know where that's going to lead you. I did a lot of this work on supercell motion when I was a journey forecaster and even a lead forecaster, so you don't necessarily have to be a SU to do all this. And of course I had a lot of help along the way. There are several objectives that we could talk about with this presentation, but I really have one main thing that I want you to get out of this, and that is I want you to be able to take a prediction of supercell motion in an operational setting and apply that to improve your short-term forecast and your severe convective warnings. As I said at the onset, supercell motion can be predicted, and severe weather and storm motion are places where we can still truly forecast. Which is why most of us entered the field of meteorology in the first place. Models aren't a lot of help here other than providing the basic wind information that we need to compute the shear and the storm motion. There are two basic parts to this presentation. The first part is some background and some theory. I'll go over that a little bit quicker so I can get to the meat of the presentation, which is in the examples. If you're going to get just one thing out of this presentation, I hope you better understand the vertical wind shear perspective of supercell motion. This is really the key. If you can understand that, you'll have a much better grasp of predicting supercell motion. I'm also going to be talking about the B2K method, which is a method to predict supercell motion that comes from a paper that I wrote along with Brian Klimowski, John Zeitler, Richard Thompson, and Morris Wiseman. If you've gone through AWOC, you'll note that that's also called the ID method. We list that in the paper as well. And it may have been called other things. But for the purpose of this presentation, I'm going to refer to that as the B2K method. So why are we here? Why even care about supercell motion? Well, first of all, we know at least 90% of supercells are severe, so we want to be able to predict them. And I think situational awareness really embodies this concept of predicting supercell motion in operation. Situational awareness is perception, comprehension, and projection. So in this particular example, do we perceive that this storm down here at the bottom is becoming a supercell? Secondly, do we comprehend what that means? Okay, its motion must change. By definition, when a storm transitions from an ordinary cell to a supercell, its motion will change. And thirdly, do we project that out into the future? Can we project now how the storm is going to move and evolve? And of course, we want to do this. We want to come up with a prediction of supercell motion before the storms even develop, so we can forecast storm relative wind parameters, and also before storms split into right and left moving components. Now, it's at this time that I ask participants to indicate where they draw a warning for this particular storm, assuming that it has just become a supercell and has become severe. So let me show you a couple answers that I've received. Some people may just go with persistence. This white arrow indicates how the storm has been moving as an ordinary cell, so they may just go with persistence. Another option is to go ahead and just draw a bigger area that you would warn for, assuming the storm may split or develop a deviant motion. So now let's go ahead and see what actually happened. Well, what we see here is that the storm exhibited a fairly climatological split with the right mover moving slower and to the right and the left mover moving faster and to the left. And I'll go ahead and draw in the arrow here which indicated the motion of the system before it transitioned into a supercell. And what we see here is if we went with persistence, the storm by and large missed that original track and went to the right and left of that. So we can see from this example why a prediction of supercell motion would be useful for situations like these. In this case, the storm split. If we anticipated that splitting, we could have perhaps put out warnings that would have focused on the areas most likely to be affected by these subsequent supercells. Okay, now that we have some motivation to understand supercell motion, let's briefly discuss some mechanisms that control thunderstorm motion. And there are really only two mechanisms, and these come from a literature review. The first control on thunderstorm motion is advection, and that's fairly simple. You're just talking about the mean wind. The second control on thunderstorm motion is propagation, and that consists of several components here. Now, in the live teletraining session, I asked several questions about these 5 propagation mechanisms throughout the presentation, so you may want to keep them in the back of your mind now, or maybe even jot them down. Anyway, these propagation mechanisms can even be interrelated. There can be several of them going on at the same time. And an understanding of these propagation mechanisms, I believe, will enable you to make a more accurate forecast of thunderstorm motion and of supercell motion. So now let's go ahead and discuss these various controls. So the first control on thunderstorm motion is advection. And again, this is fairly simple. We're just talking about the mean wind, or the mean wind layer. And the thing to take away from this slide is to understand whether or not you have surface-based storms, or if you have elevated storms that may be receiving their inflow above, let's say, 850 or 700 millibars. And the reason this is so important is because you can have very large errors in your storm motion forecast if you use the incorrect mean wind layer or mean wind depth. For example, if you have elevated storms and you use a surface-based mean wind, let's say surface to 6 kilometers, and you have elevated storms, you could have as much as a 20-knot error in your storm motion forecast. Now, as a general rule, the mean wind depth equals the lowest half of the thermodynamic profile, which means if your equilibrium level is around 12 kilometers, then a 0 to 6 kilometer mean wind might be appropriate. There's been some pretty good work done here by Richard Thompson and others down at the Storm Prediction Center talking about effective shear, effective storm relative helicity, looking just at this same concept of whether or not you have surface-based or elevated storms. Okay, so the first control on storm motion was advection. The second control is propagation. Now I'm going to talk about 5 different propagation mechanisms. The first one is that due to a supercell's rotating updraft, what I call the Updraft-Shear propagation mechanism. There are 2 key points to this slide. The first one is this. Because of a supercell's rotating updraft, it is going to propagate at right angles to the shear vector. So if we direct our attention to this upper right panel, we see we have a surface wind vector, a 5 kilometer wind vector, and if we take the vector difference between those two, we get the vertical wind shear. And so for a right-moving supercell in its rotating updraft, it's going to have a propagation component at a right angle to that shear vector, which is, again, to the right of the shear vector. And for a left-moving supercell, here in the lower right-hand panel, it's going to have an updraft-shear propagation component that is to the left, or directed toward the left of that shear vector. And of course, if you add in the mean wind to that updraft-shear propagation component, you will end up with then the resultant storm motion. Now, the second really important point in this slide is this 50% down here. And what that's saying is because of a supercell's rotating updraft, it can in effect double the updraft strength over ordinary cells. So what does that mean? Well, for example, if you have an ordinary thunderstorm with an environment of 1,000 joules per kilogram Kate, it can have a similar updraft strength to that of a supercell in an environment with only 500 joules per kilogram Kate. And that's because of that rotating updraft of the supercell really enhances the updraft strength. And this whole concept of updraft shear propagation is what is an important component of the B2K method for predicting supercell motion, which we'll be talking about in later slides. A second form of propagation is that due to a storm's gust front. And it's important to note that this is something that is internal to the storm or created by the storm. We're not talking about external boundaries here. And this gust front can be either in the form of a flanking line or it can actually get out ahead of the storm. And what happens here, if we look at this particular example, we see new cells that develop along this flanking line, and eventually they grow and they merge with this prior supercell. And as a result, they end up producing a southward propagation component. So if we go ahead and look here at the previous motion, which is this dashed line, which I've drawn in, and then we indicate the propagation due to this gust front, which is to the south-southwest because of these feeder cells, we end up with a new resultant motion that is to the southeast and a little bit slower than the prior motion. So this gust front can, in this example, actually slow the system down. as we'll see in the next animation, it can also speed a system up. So if we look at this example of gust front propagation here, we see a supercell that was moving southeast, and the gust front got out ahead of it. And because of the new development along the gust front out ahead of the storm, it acted to accelerate the supercell. And indeed, it was only moving 35 knots prior to the gust front getting out ahead of it. And when we calculate storm motion during the phase where right here where we see this gust front propagation taking place, the storm motion was more like 42 knots. And again, this gust front got out ahead of the system, which acted to force the new development in advance of the system, which again accelerated it. Yet a third kind of propagation is that due to boundary layer convergence zones. We don't want to confuse these with gust fronts because the gust front was related to the storm itself. These are external boundaries such as fronts, dry lines, sea breezes, other storms' outflow boundaries, and moisture and instability axes. And the reason these are important is because you can have enhanced moisture, instability, and convergence along these boundary layer convergence zones. And as a result, it's a favorable location for new convective development, as we see in this particular example here. And in this case, we had a supercell moving at a considerable speed to the northeast. It crosses the boundary, but we get new cell development along that boundary. It grows rapidly and then merges with the prior supercell. And the net result is an anchoring of the storm to the boundary. So you get somewhat of a multi-cell supercell hybrid. And the system motion overall is fairly slow. The cell motion, especially the previous cell that we're looking at, is fairly fast, but the system remains anchored to this boundary layer convergence zone, and this is yet a third kind of propagation. So let's look at an example of boundary layer convergence propagation. We have a boundary here with strong moisture and instability and convergence along that. We see several storms out ahead of it. And I want to circle two areas for you to focus your attention on. One is near the center of the display and one's near the bottom. Let's first focus on the one near the center. And what we'll see is that initially we had a supercell here that was moving fairly steady and fairly isolated. And then eventually we see a considerable number of new cells developing and merging on the southwest flanks of that storm. And that really slowed it down. So here's an example of this boundary layer convergence propagation. And indeed, the storm moved about 35 knots prior to this discrete development, and only 20 knots after we see the storm developing this boundary layer convergence propagation. And then another example is down here at the bottom where we have a very large cell, which indeed was a supercell, and we see a lot of development on the southwest flanks of that storm, really slowing it down. So in this case, you can see how boundary layer convergence propagation can slow a system down. There are other examples that I've seen where we say have an east-west front here, and we have a supercell moving east along that front, and you can get boundary layer convergence ahead of that storm, which will again act to accelerate it. This has a very big effect on your storm relative helicity calculations. Obviously, in this case, whether or not you use 35 knots or 20 knots can be really huge. So you really need to be aware of when this is occurring and how you calculate your storm motion. Yet another kind of propagation is that due to storm mergers. Now, this is what I call a pure example or a pristine example. We're just looking at two individual storms. Of course, we saw several mergers in the previous examples, but they were more in the form of feeder cells. But here we're looking at two storms. There's not much in the literature about this, but what I did find suggests that when two storms merge or run into each other, they tend to be influenced by the most dominant cell prior to the merger. So in this case, after these two storms merged, the most dominant one kind of dictated how they were going to move. And again, this may be best displayed by the form of an example, which we'll see next. So in this particular example, which I will animate shortly, we have a stationary supercell, quasi-stationary supercell that eventually accelerates when a new cell forms to its west and merges with it. So let's go ahead and look at this. And again, as the second storm develops to its west and merges with it, the system begins to accelerate or move eastward. And it may be that that second storm simply invigorated the cold pool or the downdraft of that first storm to get it going. Now, like I said, there's not a lot in the literature here, and I have noticed operationally cases where you have two cells that run in, are moving along, they run into each other, and then they become stationary for a while. So there's definitely some work that could be done in this area. Yet a fifth kind of propagation is that due to orographic effects. This is especially important in the western U.S., but anywhere where you have even small differences in terrain, it can be very important. And what we're looking at here is that we have an area of persistent mesoscale convergence in a given location that favors new convective development. And here are three scenarios where you have some upslope flow, or you have a terrain acting as an elevated heat source, so the flow rises up the slopes, or you can have flow around obstacles that produce, again, a persistent area of mesoscale convergence. So if we look back at this top example again, these storms may be moving at a considerable speed away from the terrain feature, but because of this area of persistent mesoscale convergence, you get continual new cell development, and that effectively can anchor a system to the terrain. So again, let's look at an example of this. So in this example of orographic propagation, let me first of all draw in the black hills right here, and then at the surface we had a wind from the southeast. At ridgetop level we had a wind from the southwest. That tends to produce a persistent mesoscale convergence region in this particular location. So what we had here was a supercell that was quasi-stationary, somewhat anchored to this persistent mesoscale convergence region, somewhat of a multi-cell supercell hybrid. And in fact, there were at least 16 first echoes that developed in this one location that continually merged on the western flanks of this supercell. And we're only seeing the end of the event. There was several hours of this going on beforehand. Another thing to note here is that we had a line of storms moving in from the west at a considerable speed. So you can have stationary storms and storms moving at a considerable speed in relatively close proximity when you have this boundary layer convergence propagation occurring. And lastly, it's important to note that we see as this line merged with this storm, it actually eventually accelerated. We're not seeing all of the loop again, but it accelerated after that merger. So up to this point, we've discussed the two controls of thunderstorm motion. You either have advection or you have propagation. Advection is just the mean wind, and propagation, we've talked about 5 mechanisms. One was updraft-shear propagation. That's important for supercells only. The others were gust front propagation, propagation due to boundary layer convergence zones, propagation due to storm mergers, and propagation due to orography. Well, now that we've discussed the controls on thunderstorm motion, let's briefly look at the B2K method. If you want to know more about that, I'll refer you to the references at the end. First of all, the B2K method was developed with 260 hodographs, and we only took into account the mean wind and updraft-shear propagation. So those other 4 propagation mechanisms we've been talking about are not accounted for by the B2K method. It's also important to note that the supercells we looked at were fairly isolated and propagated in a generally steady or continuous fashion. So if there was a lot of discrete propagation or the supercells were in a cluster or a big line, that's not generally accounted for by the B2K method. It's also important to note how it's used in forecasting, and if you use the ADA or the RUC, the B2K method is used to calculate the storm relative helicity for those models. The B2K method is plotted on the BUFKIT Hodograph display, although I do have to mention something later on about how that's done. And it's also in some of AWIPS. It's in the volume browser, but it's not in the SKUT display. It's in some of the local applications such as profiler photographs in the sounding toolkit. The B2K method is also plotted on the soundings on the real-time weather data page, and for those of you who may be familiar with the RAYOP software, it's used there as well. I also want to note that Eric Rasmussen and David Blanchard developed a technique that's similar to the B2K method, but it doesn't explicitly account for the mean wind. So let's look at how you would go about plotting the B2K method. In fact, you could go ahead and just print out this slide and use it as a guide in operations if you wish. I would hope that eventually you would get good enough at plotting it. You could just eyeball a hodograph and see where supercell motion would be without having to go through the whole process of drawing everything out. So let's go ahead and go through this. The first thing you want to do, of course, is plot a representative mean wind. That's step 1. I'll go ahead and circle here where I have the mean wind indicated with this box. That's the 0 to 8 kilometer mean wind in this example. It's just an average of the U and V components from the surface to 8 kilometers. Of course, the thing to note about step 1 is to note whether or not you have surface-based convection, elevated convection, and really paying attention to what mean wind layer you're using there. The second step is to go ahead and to draw the shear vector. In this case, it's from the boundary layer up to 6 kilometers, and this is based on the results of our study. That's why we're choosing boundary layer up to 5.5 to 6 kilometers. So I've gone ahead and I've drawn in the shear vector in the step 2 right here. In step 3, now we want to draw these updraft-shear propagation components, and to do that, you draw a line that is perpendicular to that shear vector, which we'll do right here. So we have a line that's perpendicular to the shear vector, and it passes through the mean wind, as you see right there. So what this represents is the updraft-shear propagation component. So if we start at the mean wind and go to the right, that would be the updraft-shear propagation component for the right mover. If you start at the mean wind and go to the left, that's the updraft-shear propagation component for the left mover. Now note that the distance between the tip of this arrow and the mean wind is about 7 to 8 meters a second. And that is, again, based on our study, based on the statistics, and there can be some variability about that, and we'll discuss that in later examples. Of course, here in step 3, what I have illustrated is the shear relative storm motion. If you want the ground relative storm motion, you just simply start at the origin and draw to the tips of those vectors, and you end up with the motion for the right mover and for the left moving supercell. Well, it's at this point where I'd have participants go through and actually draw up the B2K storm motion forecast, and I'll go ahead and illustrate that to you here, how that would be done. First of all, I want to note that we have the mean wind, and all these hodographs will be indicated with the big red dot. The hodograph from 0 to 4 kilometers is indicated with the blue line, and from 4 to 8 kilometers is indicated with the green line. These white circles are the winds plotted at every 1 kilometer. And so in this case, the boundary layer wind would be right down here near the surface, where I've indicated that with the X, and the 5.5 to 6 kilometer wind would be where I've indicated that with the second X. So if we go ahead and draw our shear vector, we do something like this. There's our boundary layer to 6 kilometer shear vector. Again, this is just based on the results of our study. That's why we chose that layer. And then the next thing you want to do is draw the propagation vector for the right moving supercell. To do that, you start at the mean wind, and then you go at right angles to that shear vector toward the right. In this case, we want to go about 7 to 8 meters a second. So there's that vector. Now for the left moving supercell, again, you start at the mean wind and you go to the left of the vertical wind shear vector about 7 to 8 meters a second. So let me step through this and see how I did. So here's your shear vector in the blue dotted line, pretty close, and there are your propagation components. Looks like I didn't get mine quite at 90 degrees, but you get the picture there. And then, of course, if you want the ground relative wind vector or the ground relative storm motion, you can also indicate that with these black lines. Here's a second example that I have everybody go through, and again, I'll go ahead and draw this up for you. Let me indicate where the boundary layer wind would be, somewhere down in here, and the 5.5 to 6 kilometer wind would be something like that. So if I go ahead and draw my boundary layer to 6 kilometer shear vector, it's going to look like that. If, again, I start at the mean wind and go at right angles to the shear vector toward the right, that'll give me the propagation vector for the right mover. And then if I do the same, but now to the left of the shear vector for the left mover, that's where I would expect the storm motion for my left and right moving supercells. So again, let me step through this and see what the answer is. Pretty close in the shear vector, and the propagation vector is something like that. And then lastly, here's your ground relative storm motion. It's important to note in this particular example, first of all, let me erase everything, and let me show you, here's the mean wind, generally to the east at about 7-8 knots. But the right-moving supercell motion is forecast to be to the south-southwest, so a very big angular difference between the mean wind and the forecast right-moving supercell motion. I just want to briefly mention some of the results of the B2K method, and the first thing to note is that we found that 0 to 6 kilometers was a pretty good mean wind layer based on all the statistics. That worked well most of the time. Now, there has been a recent study by Hamish Ramsey and Chuck Doswell that have suggested 0 to 8 may be a little bit better for your mean wind depth. And this could be especially true at places that are in more southern locations or where you have a deep troposphere. And of course, again, you need to be cognizant of what kind of mean wind layer you're using, especially when you get low-top storms or elevated storms. A second finding from our study, as I suggested earlier, is that this deviation of 7 to 8 meters a second away from the mean wind, either to the right or to the left of the shear vector, provided the best fit. However, there was a lot of variability about that, as noted here, from 3 to 18 meters a second. And that could be based on a lot of things, or it could be a result of the various propagation mechanisms that we're not accounting for, or incorrect storm motion calculations, bad soundings, whatever. So there is a lot of variability, and we're going to talk about this in the examples. I just want to briefly mention a couple of the strengths of the B2K method. Perhaps the most important thing is that it's shear relative, which means it's universally applicable. It can work in several locations. In fact, I've talked to people in South Africa, Australia, and Japan who have used it there. Another thing that's important to note, it works for both right and left moving supercells. And we have several left moving supercells in the U.S., and some other countries, such as Australia, have predominantly left moving supercells. And lastly, my goal of this presentation is to make you understand supercell motion well enough such that you're not going to be surprised when you see strange motions such as southwest moving supercells or stationary supercells. I think if you look at supercell motion from the vertical wind shear perspective, you won't be surprised when you see these kind of so-called erratic storm motions. Now, with any algorithm that you use, it's important to know the limitations. For example, with the radar hail detection algorithm, it's important to know its limitations. And so I also want to mention the limitations of the B2K method. And perhaps the most important limitation is that it only accounts for advection and the shear-induced propagation, which are believed to be important most of the time. However, it does ignore these other propagation mechanisms that we talked about, the gust front, boundary layer convergence, and so forth. And that's where we really come in as forecasters. We need to look at these other data sources and anticipate how these other propagation mechanisms will come into play. Another thing to note is that if you have a supercell that's showing a lot of discrete propagation, the B2K method won't be as accurate in those kinds of situations. And as a final note, the B2K method only looks at wind information. We don't take into account the thermodynamics such as the cape, the LCL height, or the precipitable water. Now, model studies have shown that these can be very important in modulating storm motion, but based on our observational database, we really haven't been able to come up with a relationship for this as of yet. So in the next few slides, I'm going to discuss with you why the shear perspective is so important. And what it really boils down to is that if you move your hodograph around, the results will remain the same after a hodograph transformation. This is not true for those methods based on the mean wind, as we'll see in the next examples. So in this first example, we have an observed hodograph, just as we've seen before. The mean wind is indicated with a big red dot. The boundary layer to 6 kilometer shear vector with the blue dashed line, which I've traced in for you here. The B2K method storm motion predictions with the blue X's, and the right mover is I have underlined here. And those storm motion methods based on the mean wind I have circled right here, the two smaller red dots. So what we want to note on this particular slide is that the B2K method has a forecast supercell motion for the right mover that is to the south-southeast of the mean wind. The methods based on the mean wind, the 20R85 and 30R70, are to the south-southwest of the mean wind. In this next hodograph display, all we have done is taken the previous hodograph and shifted it 10 meters a second to the left. Otherwise, we have the same shaped hodograph. Now, if we look at the B2K method prediction, we see it is to the south-southeast of the mean wind exactly as it was before. Those methods that are based on the mean wind now have shifted their prediction, and they are just slightly to the south of the mean wind. Well, let's just take this one step further now. In this third example hodograph, all we've done is shifted the previous hodograph another 10 meters a second to the left, so now it's a full 20 meters a second to the left of the original hodograph. Again, it's the same exact shape. If we look at the B2K method prediction, it's still to the south-southeast of that mean wind. But now the methods that are based on the mean wind have a prediction that is to the east-northeast of the mean wind. And this doesn't really make sense because the hodograph shape has stayed the same, the shear has stayed the same, so the storm dynamics should stay the same with all three hodograph shapes, but you see the motion has changed just because we shifted the hodograph around for these methods out here that are based on the mean wind. However, the B2K method kept the same predicted storm motion relative to the shear profile for all three examples. And this really drives home the point of the shear relative perspective of supercell motion. Well, let's look at a different hodograph example. And first of all, draw in the boundary layer to 5.5 to 6 kilometer shear vector right here. And we see the mean wind in the big red dot and the observed storm motion in the purple diamond. The observed storm motion wasn't to the right of the mean wind or to the left. It was generally faster, or it moved away from the mean wind. And if we look at the predicted supercell motion, again, you start at the mean wind and go 7 to 8 meters a second to the right of the shear vector. We see that was pretty close to the observed storm motion. So again, the storm moved to the right of the shear vector, but it moved away from the mean wind. In this final hodograph example, we see a storm that moved much slower than the mean wind. First of all, draw in the boundary layer to 5.5, 6 kilometer shear vector right here. We see the mean wind, which was about 20 knots, fairly significant. The 0 to 6 shear, about 40 knots. Again, a fairly vigorous environment. But the storm motion was only about 5 knots. The predicted supercell motion was, again, to the right of the shear vector. You start at the mean wind, go to the right of the shear vector, about 7 to 8 meters a second. So that gave you an indication that you were going to have a slow-moving supercell. So I hope you can see from this example and the previous examples why forecasting supercell motion to the right of the mean wind can fail. And in this case, actually, the supercell moves slower than the mean wind, perhaps a little bit to the left of it. Another thing to note from this example is that you can use a hodograph from the vertical wind shear perspective to anticipate slow-moving supercells. Again, here we had fairly strong shear, strong mean wind, but the storm moved, in effect, against the mean wind. But you can anticipate that with the B2K method and by looking at the hodograph from the vertical wind shear perspective. Okay, we're about halfway through the presentation. Now we're going to move on to the examples. Up to this point, we've looked at some background materials for understanding storm motion in the B2K method. Next, we're going to apply this to some real-world situations. And again, the two controls of thunderstorm motion are advection and propagation. We talked about 5 supercell propagation mechanisms. They were updraft-shear propagation for supercells only, gust front propagation, propagation due to boundary layer convergence zones, propagation due to storm mergers, and propagation due to orography. Then we talked about the B2K method and noted that it only takes into account advection, or the mean wind, as the first component, and the next thing it accounts for is the updraft-shear propagation, but it doesn't account for the other 4 propagation mechanisms. First of all, if you're going to plot storm motion in AWIPS, you can do that with the volume browser. You may have a little bit different setup than what I'm showing here, but all of you should have a button that says Convect somewhere on there, and under that you will be able to select the right moving supercell and left moving supercell buttons. And these are baseline fields, so they should be in everyone's volume browser. After you select those, your layer plane over here should highlight automatically. And then what I suggest is going ahead and using the RUC 40 on the state scale, so that way you can load your radar data and then load these storm motion vectors, and they will time match. And then if you want to load your mean wind, you just go and load your wind, or select wind just like you were choosing the surface or the 500 millibar wind. The only difference is then you come over here under the height plane, and you can choose 0 to 6 kilometers or 0 to 4, 0 to 8 if they are actually in your volume browser. This first example really epitomizes what I've been talking about regarding situational awareness and predicting supercell motion. And this is an actual event a forecaster here at Rapid City experienced. He had several challenges. The first one is, how is the storm going to move as it became a supercell? And the next one was, how long was the storm going to last? I want you to note, or want to note, that please don't focus on what part of the country these examples come from. That's not important. What's important is the process or the concept, and I've intentionally left CWA boundaries off because of this. These results should be universally applicable. Well, here's a hodograph that came from about midway through this event, and first of all I want to illustrate the B2K method. You start by drawing your boundary layer to 5.5 to 6 kilometer shear vector, which I've illustrated here with the blue dotted line, and then I retraced with the purple arrow. The second thing you do is you start at the mean wind and go to the right of the shear vector, about 7 to 8 meters a second on average again. Then you start at the mean wind and go to the left of the vertical wind shear vector to find your left moving supercell motion. Of course, if you want the ground relative storm motion, you can simply just start at the origin and go to the tip of those arrows. So for the right mover, you would expect a south-southeastward motion. I also want to note about this case is we have 60 knots of shear over the lowest 5 kilometers, so that's very strong, about double the values observed for low-end supercells. We're going to look at an animation of the pre-supercell phase here, but the first thing I want to point out is that on all of these slides down here there's going to be a legend, and what that shows is that we have the green vectors representing the forecast supercell motion from the ruck for the right mover. The orange or tan vectors represent the motion of the left moving supercells, and the cyan vectors represent the mean wind over the lowest 0 to 6 kilometers. So in this particular animation here, we're plotting the mean wind from the ruck from 0 to 6 kilometers. And what we see is we had ordinary cells moving to the east-northeast, and then towards the very end of the display, or at the end of the animation, we see that the supercell intensifies a little bit and appears to be changing its motion. Now it's at this point when I would ask a participant to indicate how this storm is going to move. Actually, I'd have them draw up a box for a warning. And so I've gotten several examples. One might be to, now, nobody's really gone with persistence, but some people will draw a box that'll go something like this, kind of to the east-southeast. Other people will take into account the previous hodograph that showed the supercell moving to the south-southeast. So there's a couple examples you might use. And one thing I want to point out here is when you're using Warren-Gen, note that the storm had been moving from the west-southwest, generally to the east. So if you're going to use the past position in Warren-Gen, what you're going to end up with is a box that's actually out to the kind of toward the east here. And if you want to come up with a different box that would be to the south-southeast, you really have to play with your path cast dot with Warren-Gen and put it in a previous location where there isn't any storm or where there wasn't any storm in order to get your box to come out like this. So it's something you may want to practice with Warren-Gen. I just want to show you here that indeed the storm was a supercell. The radar perspective is looking in from the left, and we see that we had fairly strong outbounds and strong inbounds here, strong counterclockwise circulation. This had persisted for a couple volume scans and at 2 different levels, so we definitely know that the storm has become a supercell, and by definition, when a storm transitions from an ordinary cell to a supercell, its motion must change. That's just the way supercells operate. So as we look at this animation here, we see that the storm took a very hard right turn, and this animation picks up right where the other one had left off, and we see that when it transitioned into a supercell, it moved pretty much due south. If you look at the green arrows up here at the beginning, the ruck had a pretty good idea of that, and of course we saw that in the hodograph showing a south-southeast motion. Storm moved it a little bit farther to the right of the shear vector up there, and then even toward the end of the loop, if we notice the green vectors show a south-southwest motion. So the ruck did a pretty good handle, had a pretty good hand on this, did a pretty good job of picking up this hard right turn up for the supercell. So if we look at a satellite animation of this, we see that there was a north-south instability axis in here. The yellow dashed lines represent the lifted index, and the storm moved somewhat along this instability axis. And I believe part of that is due to the fact that the shear profile suggested you would have a southward moving supercell, and since it moved along this instability axis, it lived a lot longer than it would have, let's say, for example, if the storm would have been moving toward the east. It would have been moving away from that instability. If you don't have good visibility where you live, this is what the storm looks like when you have good visibility about 100 miles away from our office. It was a very significant storm with 10 large hail reports and 1 2 3/4 inch hail report. Now let's go back and look at the hodograph from the beginning of this example. The only difference here is I've just plotted the observed storm motion on this. And we see again the B2K method forecast to the right of the shear vector about 7 to 8 meters a second. And as it turns out, the storm moved a little bit farther away, about 9 to 10 meters a second away. And I think part of this is due to the fact that you did have very strong shear, and so you could have had a stronger updraft-shear propagation component, a much stronger supercell circulation, and that caused the storm to propagate farther away from the shear vector. Well, this first example shows that the supercell motion was reasonably well forecast, and it was a little bit farther to the right of the shear vector than predicted, but not too far. And part of that deviation could have been due to this updraft-shear propagation. So instead of the typical 7 to 8 meters a second to the right, it was more like 9 to 10. We didn't notice any of these other propagation factors being important. The hodograph suggested a southward moving storm motion, which was along this instability axis, and indeed the storm lasted about 5 hours, and that, because of the coincidence of these two, may have led to the longevity of the storm. The most important part of this case is that the forecaster's situational awareness was enhanced. First of all, he perceived the storm was becoming a supercell. Secondly, he comprehended what that meant, i.e. that the storm motion would change. And thirdly, he projected that out into the future to see that the storm would move toward the south, it would be along this instability axis, and therefore he put out a warning accordingly and kept staff for a much longer period of time, or anticipated the need for staff to stay longer. Now, I also want to note that this storm was by and large in the middle of nowhere, but what if it was a storm that was in your CWA just upstream of a major city, and you had to make this decision of, is this storm going to hit my populated area, or is it going to move to the south of it and miss it? And that's where this forecast of supercell motion in operations can be especially useful. In the previous example, we looked at a supercell that took a very hard right turn, but in this example, we're going to see some supercells that exhibited a gradual right turn or some curving tracks, and we'll see how well the RUC 40 captured that motion. Here are the supercells as they appear in reflectivity. We're actually going to look at a storm total precip animation. Well, as we can see in this animation, the supercells start out at the top and they move toward the south. Let me go ahead and trace out their tracks. The first one, which was the longest lived, moved southeast and then eventually toward the south here. The second one didn't last as long. It started out moving southeast and then curved back toward the east in the direction of the mean wind, and it did that as it was weakening or losing its supercell characteristics. You can see how this could be very important for doing short-term forecast, as at the beginning up here of this longest-lived supercell, if you were to put out a short-term forecast and go with persistence on the pathcast, you'd have something that eventually would get off track. But if you looked at the green arrows from the RUC, which represent the forecast supercell motion, and if you use that as guidance, you would get the idea that the storm would indeed exhibit a gradual curving track. And this could be used then to help you make a more accurate short-term forecast. Here's a composite hodograph from about midway through this event from several sites, and I just want to illustrate the B2K method once again. First of all, you draw your boundary layer up to 5.5 to 6 kilometer shear vector. Next thing you want to do is you start at the mean wind and go right of that shear vector about 7 to 8 meters a second. So there's your shear relative storm motion. Of course, if you want your ground relative again, you start at the origin and draw to the tip of that arrow. So you see that overall this event was pretty well forecast by both the RUC and then the observed hodographs. In this next example, we're going to be looking at some left-moving supercells, and this was especially important because this is a case where we didn't have velocity data, and we compared the observed storm motion to the forecast left-moving supercell motion to help verify that we actually had supercells. And again, this is an actual event that a forecaster here worked, and he used it to identify the storm as being a supercell versus, let's say, a strong multicell. This can be especially important in the west, too, where you don't have as much radar coverage. You have reflectivity coverage, but you don't have velocity data everywhere, and you can use this to help identify the presence of supercells. So let's go ahead and look at a satellite perspective of this particular left-moving supercell. It displayed a storm split, which you can see here in the satellite imagery. Actually, you can observe it right after it experienced its split, and I have that indicated with the pointer. I'll go ahead and stop this. There's a couple interesting things that we see in the satellite display. First of all, we have a cloud boundary or a cloud line right in here separating two air masses. To the northeast, we see some stable billow clouds, and the reason we note that they're stable billow clouds is, number one, they're fairly smooth, and number two, we see that the surface wind is oriented at an angle to those clouds. Now, to the left or to the southwest of this cloud line, we see what appear to be horizontal convective rolls, and notice how they are generally aligned in the direction of the surface wind. That's a giveaway that you have horizontal convective rolls, and they also appear more bumpy or more unstable. So just by looking at the nature of the clouds, you can infer what the stability is in this area. Well, now let's go ahead and look at the radar animation of this left mover. I'm tracking it with the distance speed tool right after the storm split, and you'll note that if you compare the observed storm motion with that of the orange or the tan vectors, which represent the left-moving supercell motion that's forecast from the RUC, you see it's pretty close between the observed and the forecast. And indeed, this helped the warning forecaster identify this storm as a bona fide left-moving supercell and gave him more confidence in his warning. And it turns out the storm did produce some golf ball-sized hail. Now we're going to look at a hodograph displayed with BUFKIT. And first of all, I'd like to note that BUFKIT's an excellent tool, and you should all be running it at your office. There's a lot of things that you can do with it. But for this particular case, I'm showing you a 0 to 3 kilometer hodograph. The B2K method is plotted here. You can see the R for the right mover and the L for the left mover, and then the M for the mean wind. But the important thing to note about this is that this is a 0 to 3 kilometer hodograph, and if you have 0 to 6, I think it actually goes out something like this. So the mean wind should be more over here, a little bit stronger to the east-northeast than what it's showing. And the reason that's the case is that the way BUFKIT calculates the mean wind, it uses all available levels. So if you look over here in the bottom right, you see there's a lot of levels concentrated in the lower part of the profile because you're looking at the RUC and it's got a lot of levels down low. And that biases the mean wind toward the lowest few kilometers of the profile. Now, when we calculate the mean wind with the standard B2K method, we take wind at equidistant levels, so let's say every 500 meters, so we don't have this bias towards the lower atmosphere. So you need to be careful when you're using BUFKIT and looking at the B2K method because in general the storm motions will be a little bit slower than what they should be just because the mean wind is not calculated as we suggest. In this next example, I'm going to highlight a potential weakness with the B2K method, and that is when you get supercells developing along a boundary, especially a strong boundary, that can really affect the storm motion. And we're also going to be talking about what kind of feature do you track when you calculate storm motion, and what is most relevant for storm motion. Are you looking at the cell motion, for example, or the system motion? And we'll look at several examples of that. Here's a little bit of background on the environment. This hodograph comes from east of the event, but what we see is that the storm motion was forecast to be to the south-southeast, and again, if you go ahead and plot up the B2K method, we draw the boundary layer to 6 kilometer shear vector. You start at the mean wind, you go to the right of that shear vector, 7 to 8 meters a second, again, on average, and there you end up with your forecast right-moving supercell motion. And for the left-moving storm motion, that's something like this to the left of the shear vector. It's also important to note that we have fairly weak winds aloft, storm relative winds that is, and that would suggest you may have a tendency towards high precipitation supercells. The storms that developed on this day developed right along or just ahead of this boundary. There was a lot of moisture and convergence and instability along this boundary. Not much of a cold front, more or less just a wind shift line. And it's also important to note about this is that when you get supercells developing along these strongly convergent boundaries or well-defined boundaries, they can definitely present a challenge when forecasting supercell motion. We're going to go through a series of animations here where we look at 3 separate right-moving supercells. In this first case here, is right after the storm split. So we have the left mover that was moving to the east and the right mover that was moving toward the south-southeast. And then there was another new storm developing rapidly along that boundary. Now, note that these cells are not isolated from one another, definitely increasing the chance for storm mergers. Here's a storm relative velocity image from the same time as the previous. Just want to point out the circulations. Here we see the clockwise circulation of the left mover. Here's our counterclockwise circulation of the right mover, number 1. And there's also a second very weak clockwise circulation just to the north of that. And indeed, there is a left mover trying to split off from this right moving supercell, and it turns out it didn't last very long. And also note that your radar perspective is looking in here from the north-northeast. In this first animation here for RM1, I'm trying to track the continuous or quasi-continuous cell motion, the part of the storm that's most steady. So notice here we see it moving to the south-southeast, but there are also some other storms or cells trying to feed in on the west side. But again, I'm trying to track this discrete supercell as it was moving to the south-southeast. Okay, now moving forward a little bit later in time, we see that RM1 now is getting to the point where it's mature, it's going on to its weakening stage. RM2 is the newest supercell, which is growing very rapidly, and yet we have additional cells forming along this boundary. So we got a lot of things going on right along this boundary here. Here's the storm relative velocity for the same time. Now we're looking in from the southwest. We see that the counterclockwise circulation still exists for RM1. For RM2, we see that there's a fairly tight circulation right there, and there is not yet any circulation with those new cells that are forming up. So now let's go ahead and look at the animation of RM2. Well, in this animation, like before, I'm trying to track the steady or the continuous propagation of RM2, which is to the south-southeast. And we saw in the velocity data that we definitely had separate circulations here. But you will notice that there's a lot going on here. There's storms that are trying to develop or feed along this boundary into the west side of RM2. Okay, well now we're moving on to the third phase of this example. We can see that our old RM1 is pretty much weakened and it's lost its circulation in the velocity data. RM2 is mature to going on to its dissipating phase. And now we have a new cell, RM3, that is growing rapidly along that boundary and has become a supercell. And when you look at this, you might want to ask yourself, is this just one big supercell or is it 3 distinct cells? And of course, we've seen in the velocity data that these are indeed separate supercells. Here's the velocity data for the same time as the previous slide. Again, the RM1 circulation is totally gone. The RM2 circulation is showing up right here. And then RM3, again, a small but fairly tight circulation right there. So we are showing the separate circulations. Again, the radar looking up here from the south-southwest. Here's the animation for RM3. This is just like before for RM1 and RM2. I'm trying to track the steady or the continuous propagation of this supercell. It's more or less quasi-continuous because you do see there's a lot of stuff going on here. There's cells developing on its western flanks trying to feed in, and it's also very close to the previous supercell RM2. Okay, up to this point we've tried to track the continuous propagation, but right here I'm going to go ahead and animate the entire event, and we're going to track the discrete propagation. So let's go ahead and look at this. This is what it looks like if you're going to track the whole complex as just one big storm. So you're tracking here the system motion, not the cell motion, and you're tracking all this discrete propagation. So again, you look at this and you say, well, doesn't it look just like one big storm? But in fact, we do know by looking through this several examples here that these were separate supercells. Well, here's the satellite perspective, and it shows much the same as the reflectivity data in that you had a lot of discrete development. What we see are some overshooting tops along this boundary. In fact, they They develop quite rapidly and overshoot to the southwest along this boundary, so definitely a sign that you had some discrete propagation going on here. Well, now let's go ahead and look at the hodograph from earlier. Let's first focus here on the left, and in this display I've plotted the continuous storm motion that I tracked in the 3 animations, and that's indicated right here. So we see the predicted storm motion to the right of the shear vector, and the observed, which is just a little bit farther to the right. So not a big storm motion error, but there is just a little one there. Now on the right hodograph display, we're tracking the discrete storm motion, which is more like the system storm motion. Again, the predicted supercell motion is right there. The observed was much, much farther to the right over there. So we see a big difference if we're tracking the cell motion or the system motion. Now, based on previous discussions, we believe it's this cell motion or the continuous motion that is most important for storm relative helicity, because that's what the cell is seeing. If you look at the system motion, it's not really what the individual storms are seeing. So it's probably best to look at the continuous storm motion when calculating storm relative helicity. Another thing to note here is that you may ask what other propagation mechanisms were at play. I mean, we know advection was important. It's important for almost all storms. The Updraft-Shear propagation was important because we had supercells, but what about the other 4? And when we think in terms of the gust front, that may have been important. The storm's gust front may have been lifting new cells along that boundary. Definitely the boundary layer convergence zone was contributing to new cell development and some propagation. Storm mergers appeared to be going on along that boundary. The only other thing that probably wasn't acting was orography, as this is relatively flat country. Well, here's the same hodograph again, but now I've plotted the left-moving supercell motion, and what we see is that it was fairly close to the predicted supercell motion. I think there's maybe a couple reasons for this. First of all, the left mover didn't indicate any kind of discrete storm motion. And secondly, it was moving away from that strong boundary, so it wasn't experiencing that boundary layer propagation or that strong convergence that the other cells were experiencing along the boundary. So for this event, what we saw was both continuous and discrete propagation, and we really focused on how do you calculate storm motion, and we saw both ways can be calculated. Also highlighted some weaknesses of the B2K method, and especially when you have supercells that are propagating discretely, the B2K method won't be as effective. And again, I want to reiterate that the B2K method was developed with mostly isolated supercells that had a continuous or a steady kind of propagation. And then the second thing to note out of all this is that advection and shear-induced propagation are accounted for by the B2K method, but not the gust front propagation, not the boundary layer convergence or the mergers or the orography. And that's where we really come in as forecasters. I think knowledge of these potential propagation mechanisms due to gust fronts, etc., is especially important for us as forecasters to be aware of. And then lastly, I think cell motion is more relevant for the storm relative helicity calculations, and you can definitely come up with some very different answers whether or not you use cell motion or system motion. Now we're going to change gears a little bit and move toward the south. Here's another example of a left-moving supercell that was elevated and produced quite a bit of severe weather over the eastern portion of Arkansas. This long track of hail reports all came from this one elevated left-moving supercell. Here's a little background on the environment. The 12Z and 18Z soundings for Little Rock showed that you had some elevated instability. You definitely weren't going to get surface-based convection out of these, but you can see here at about 1,000 meters you had some elevated instability ranging from about 1,000 to 2,500 joules per kilogram. The observed hodograph, 12Z from Little Rock, suggests that your right-moving supercells would move generally to the east and the left movers would move fairly rapidly to the northeast. And notice that there's quite a bit of shear, and there's also quite a bit of curvature here in the low levels, what we see right here. And so you may be asking yourself, say, well, gee, we had left-moving supercells on this day. Why did they occur if you had all this low-level curvature? And I think the answer to that question is because the storms really weren't seeing all this shear here in the low levels, because they were indeed elevated and they weren't getting that surface air ingested into the storm's updraft. An animation of the reflectivity on this day shows this left-moving supercell that moved fairly rapidly up the eastern side of Arkansas. There were a lot of other storms around this particular left mover, but it was definitely the most dominant, and it produced almost all those hail reports there. Also of interest, there were several right-moving storms here to the south that were produced some significant tornadoes. They were near a warm front, and there is a west case that has been developed by Jeff Craven for that event. Let's look back at that hodograph from 12Z at Little Rock, and the only difference here now is I plotted the observed motion of the left mover. We see that there's a storm motion error of about 5 meters a second. It's significant, but it's not as big as it could be. I've seen cases where we've had 10 meter a second errors by using incorrect mean wind. When I've used a surface-based mean wind when it should have been elevated, I've had 10 meter a second errors before, so they can be quite large. Well, we know that the supercell, the left mover, isn't seeing all this shear in the low level, so let's modify this hodograph to account for that. Well, what we have here is the modified hodograph from 12Z, and all I did is essentially chop off the lowest 1,000 meters. So now what is labeled here as the surface wind really is the wind at 1,000 meters, and the 8 kilometer wind is really at 9 kilometers. So I just shifted the hodograph 1,000 meters up from the surface. And so what we see now is the storm motion error is not as significant as in previous, number one. And the second thing we note here is that the hodograph is essentially unidirectional, which supports the existence of that left-moving supercell. And again, I refer you to some of the work that Richard Thompson and others at SBC have done regarding effective shear, effective storm relativisticity, and discriminating between these surface-based and elevated storms. And their work shows up in the 22nd Conference on Severe Local Storms. One thing I want you to get out of this event is that, again, the standard 0 to 6 kilometer mean wind is not always the best. I mean, sometimes 0 to 8 works better, and sometimes you have an elevated storm, so you may be using 1 to 5 or 1 to 6. So the whole key in all this is to be operationally aware, have your situational awareness enhanced, and pay attention to what kind of storms you have and what kind of advection layer they're moving through. Another thing is that you can have these elevated storms moving well north of a boundary producing copious amounts of hail, even though the surface is very stable. So you have to keep your eye out for those kind of storms. In this next example, we're going to look at some very large supercells that moved across northern Texas and produced some big hail and some strong winds. And again, I want to illustrate one of the weaknesses with the B2K method with this example. Here's a hodograph from Dallas during the event, and we see that the boundary layer to 6 kilometer shear vector points to the northeast. And we had very strong shear in this case. We had about 65 knots on the lowest 6 kilometers, so very strong shear. The predicted storm motion, again, you start at the mean wind and go to the right of the shear vector, 7 to 8 meters a second. And again, this represents your updraft-shear propagation. It's a fixed value, 7 to 8 meters a second, based on our study. And again, there's a lot of variability about that value, and that's why I want to show you this particular case. Well, here's an animation of these supercells that moved across North Texas. The first thing you'll probably note is they're fairly large, fairly wide supercells, so they're obviously very strong. Some of the cross sections revealed large B weirs, which again indicates a strong and wide updraft. Note that the continuous propagation appears to be the dominant mode here. I really don't see any discrete propagation. There's a couple storms that split apart, but I'm not seeing a lot of feeder cells or discrete propagation occurring. So continuous propagation appears to be the dominant mode, which would suggest that B2K should work fairly well. Well, now let's look back at that Fort Worth hodograph. Same as before, except now I've plotted the observed storm motion. And we see that the predicted motion was to the right of the shear vector as such, but the observed was about double the distance away from the mean wind to the right of the shear vector. Now, since we saw it was mostly continuous propagation, not much in the way of discrete propagation, I wouldn't think that orography would really be a big factor. We couldn't really see the gust front, but it didn't look like there was a lot of development along the gust front that would take it more to the south. And storm mergers really didn't seem very apparent, and we didn't notice much in the way of boundary layer convergence propagation. So By way of deduction, I would suggest that most of this error here from the distance between the forecast supercell motion and the observed was probably related to a stronger updraft-shear propagation component or a stronger rotating updraft. Note that the storm deviated farther to the right of the shear vector. And indeed, I talked to Morris Wiseman about this, and when he's done some modeling studies and he progressively increases the vertical wind shear, as I'll draw right here, with stronger shear you tend to get farther propagation to the right of the shear vector based on the modeling studies. And there's also been some work done by Robert Davies-Jones down at the University of Oklahoma that suggests that you have stronger off-hodograph propagation as the storm's updraft width increases. So in this case, we had a couple things occurring. Very strong shear and wide updrafts, which I think engendered a much stronger updraft shear propagation component. So this just shows you the standard 7 to 8 meters a second to the right for the right mover isn't always going to work, and you're going to have to be aware of that and modify that on the fly if you're aware of what's going on. Just to summarize this example once again, we had a fairly strong deviation from the mean wind, and I believe part of that was related to that updraft shear propagation. Note that the B2K method uses a fixed value that's based on the statistics, based on our study, so you need to be aware of when you may want to modify that for larger or smaller values, and hopefully these examples are showing you how you might do that. In this next event that we're going to look at, there was a pretty good severe event over Arizona with monsoonal flow and somewhat of an atypical wind pattern. And I think a sheer relative perspective of supercell motion is especially needed for situations like these, as we'll see in the radar animation. As we look at this animation, you'll notice that some things appear rather bizarre. You got left movers that are moving to the south-southeast, right movers that are moving to the west. And you look at that and you say, gee, that really doesn't make a lot of sense. How often do right-moving supercells move to the west and left-moving supercells move to the south-southeast? That really doesn't make a lot of sense. However, when you look at the hodograph from the vertical wind shear perspective, things become a lot clearer. So here is the hodograph from Flagstaff. First of all, I want to draw the boundary layer to 5.5 to 6 kilometer shear vector right there. Note that this is pointing to the southwest. Now if we start at the mean wind and go to the right of the shear vector, we have the predicted motion for the right moving supercell. You start at the mean wind and go to the left of the shear vector, and you have the predicted supercell motion for the left mover. And now you see that these are reasonably well related to the observed storm motion. So everything becomes a lot clearer once you understand the supercell motion from the vertical wind shear perspective. But just looking at the radar animation without any knowledge of the vertical wind shear, things look rather confusing. Another thing to note about this is that this hodograph, although it has enough shear for supercells, it was just barely enough. And I want to point out that you need to make sure you do have enough shear before you apply the concept of predicting supercell motion, because if you don't have enough shear to get supercells, it doesn't make much sense to try to predict how supercells are going to move. Well, now we're moving on to our final example here, and this comes from the University of Maryland tornadic event, if any of you are familiar with that. Well, here's some environmental data that comes from the RUC. I didn't have any good observed data for this case. First of all, we'll look at the sounding. We'll see it's a fairly moist and unstable profile. The thermodynamic depth is about 12 kilometers, so you'd expect 0 to 6 kilometer would work pretty good for your mean wind depth on average. Now, I do want to point out that this Cape profile is fairly thin here, and thin and tall, so maybe that would suggest you may have some lower top supercells. It's something to keep in mind. I also want to note here on the hodograph display, we have the predicted right-moving supercell motion to the northeast at about 30 knots. We're going to look at two supercells from this event. The first one I'm going to call Supercell 1, or SC number 1, and we see here it's tracked here with the distance speed tool. It shows a motion, an observed motion of 21 knots. And you can compare that to the green vectors, which again represent the right-moving supercell motion forecast using RUC 40 data. And so you may ask yourself, well, why is there this 10-knot difference? You have an observed motion of about 20 knots and predicted about 30 knots. Well, I want to point out to you that the echo tops on this particular supercell were only up to 25,000 to 30,000 feet. So it is quite likely that the 0 to 6 kilometer mean wind layer is not appropriate for this particular storm. Indeed, something like 0 to 4 would be much more appropriate because we have a low-topped supercell here. Now we're moving ahead a little bit, about an hour and a half, and here's another supercell that occurred on this day to the southeast of the previous one, and we see that this one, based on the distance speed tool, is moving at a speed of 30 knots to the north-northeast, which is a lot closer to the predicted motion from the hodograph we saw earlier and also what the RUC is showing here with these green vector overlays. Not surprisingly, this supercell had echo tops of 45,000 to 50,000 feet, so it's much taller than the previous storm, consistent with advection over a deeper layer. Well, now we'll look at the hodographs from this event. First, let's look at the upper left. And what I have plotted here is the standard B2K. The mean wind is from 0 to 6 kilometers. The forecast supercell motion is here about 30 knots to the northeast, and we see the observed motion for supercell 1, which was around 20 knots. We ended up with about a 5 meter a second storm motion error. However, recall that this storm up here, supercell 1, only had tops of 25,000 to 30,000 feet. So what if we use a shallower layer for your mean wind, which I do in the lower middle display? This mean wind is calculated over the lowest 0 to 4 kilometers, and we see now that the observed motion of supercell 1 and the predicted motion of supercell 1 are much closer. And again, that's using a modified B2K method with a 0 to 4 kilometer mean wind. Now if we look in the upper right-hand display, this is the same hodograph as we saw at the beginning with the 0 to 6 kilometer mean wind and the B2K method predicted based on that 0 to 6 kilometer mean wind. Now we see that the observed motion of supercell 2 and the predicted motion are much closer together. So again, you need to be aware of what kind of storms you have in your environment, whether or not they are low-topped or they are your typical tall supercells. One thing I want to point out from this event is that you need to be continually aware of what your mean wind depth is, and you may have to adjust that. Now, this rule of thumb of using half of the thermodynamic depth works good as a first guess, but as we saw in this case, it didn't work for all storms, so you need to be aware of that. Also, when you use the AWIPS volume browser to plot supercell motion, it uses this fixed depth of 0 to 6 kilometers. That's kind of hard-coded into the algorithm. So if you want to use something different, you're going to have your AWIPS focal point adjust that. I also found it especially interesting that you had low-top supercells and tall supercells occurring on the same day that were not very far apart from each other in both time and space. And here's where your situational awareness really needs to be enhanced for something like this. Well, that brings us to the end of the examples. As I've gone through this presentation, I hope I've been able to impress upon you the importance of the vertical wind shear perspective and how that applies to supercell motion. It's kind of like when you learned how to ride a bike. Before you could ride a bike, you struggled, it was difficult, it didn't appear that easy, but once you finally learned how, everything just fell into place for you. It really clicked. And I think you'll have that same kind of awakening when you understand the vertical wind shear perspective. Supercell motion will just make a lot more sense for you. And we also spent quite a bit of time talking about the B2K method. We said that it's comprised of advection and shear-induced propagation. We think they're dominant most of the time in controlling supercell motion. Of course, there are the other propagation mechanisms, but you really can't account for them with the hodograph. We also spent quite a bit of time plotting up the B2K method, and I would expect that the more you do that, the more experience you gain, it will become just second nature to look at a hodograph and spot where the storm motion should be. I think the benefit of overlaying the mean wind and the forecast supercell motion on radar data cannot be overstated. And in fact, I have an assignment for you. I want you to go out after this presentation and operations, develop a procedure to overlay radar data, supercell motion forecast, and the mean wind. And again, I suggest using the RUC 40 on the state scale as a starter. So load your radar data and then your storm motion forecast and mean wind. I believe you will see improvement in your short-term forecast and your severe convective warnings if you do this. And it will also help you highlight these so-called erratic storm motions where you get southwest moving supercells or stationary or potentially flash flood moving supercells. So here's what I would recommend you do in operations. First of all, go ahead and use the B2K method as a starting point, the standard B2K method. After that, you really need to determine if your mean wind is going to be 0 to 6 or if it's going to be modified from that. Are you going to have low top storms, elevated storms, etc.? After you've done that, you need to be really aware of these other propagation mechanisms that we've talked about throughout the presentation. Understand how they can influence thunderstorm and supercell motion. And that's really where we come in as forecasters, is we want to understand how these other mechanisms can apply and can affect storm motion. I think if you have a solid understanding of all these, that will really help you in the severe storm setting. It may also be useful to overlay the B2K supercell motion forecast on satellite imagery, because that can perhaps help you identify some of these propagation mechanisms. And lastly, keep in mind that this supercell motion will change in time. We saw that with the storm total precip animation. The shear changes in both time and space, so your storm motion isn't necessarily going to be constant. As I said earlier, if you want to know more about the background of the B2K method, I'd point you to this very first bullet here, and it talks about how the method was developed. A lot of this presentation we just talked about here today comes from this paper that's going to appear in the National Weather Digest, and there actually is a PDF of that paper online. It has a lot of these propagation mechanisms that we talked about and some other examples. Some people like to brush up on hodographs, and I would suggest that you look at these two yellow bullets. They give really good information, some background information on just plotting hodographs and interpreting them. I want to point you to a couple resources that are available. If you go to the student guide page, you will be able to find a PowerPoint presentation of this particular teletraining. You will also be able to find an Excel spreadsheet where you can plot up hodographs, as you see here. This is what you will find on the web page. And when you use this spreadsheet, you can plot up your wind information in this yellow box and these yellow boxes here. It can be either the direction of the speed or the U and V components. It can be in either knots or meters a second. You can also adjust the deviation from the mean wind for the B2K method, so you can make it 3 meters a second or 15 if you wish. You can adjust your mean wind depth for tall or shallow storms. You can also make it so that it will display the hodograph for an elevated layer. So if you want to chop off the lowest 1,000 meters, you can do that if you have elevated storms. There's a place where you input the observed storm motion, and also to compare that to the predicted, it will give you the error in the storm motion forecast. And of course, if you have any questions about using the spreadsheet, please contact me. I'd be glad to help you out. And don't worry about breaking the spreadsheet, because if things get messed up in it, just go ahead and download a new copy. I want to leave you today with just one final thought, and that is supercell motion can be predicted. We've been doing it here, like I said, operationally since 1997. And I firmly believe that if you go out and develop the procedure like I recommended, you apply the concepts that we learned here today, ultimately you will produce better short-term forecasts and better severe convective warnings. And like I said earlier, if you have any questions whatsoever, please feel free to contact me, and I'd be glad to discuss them with you. Thank you once again for your attention.